Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. Modeling the Carolina Bays. Hello, I'm Antonio Zamora. In this video I present various physical models that have been proposed to explain the formation of the Carolina Bays. The most important features of the Carolina Bays are their elliptical geometry and their radial alignment toward the Great Lakes. Even though the bays can range in size from a few hundred meters to several kilometers, they have fairly constant width-to-length ratios and maintain their shape even when they overlap. I hope that this video encourages experimental geologists to design and refine the equipment necessary to reproduce the geomorphology of the Carolina Bays under controlled conditions in the laboratory. Milton and Shriver in 1933 suggested that the Carolina Bays could have been formed by extraterrestrial impacts. Douglas Johnson disagreed. In 1942, Johnson proposed that the bays formed by a complex combination of wind and water processes. At this time, all of this was theoretical. It was only in 1952 when William Prouty conducted experiments to test the impact hypothesis. Prouty fired a high-powered rifle at a powdery target to produce somewhat elliptical depressions. These images show the results of bullet impacts on plaster of Paris powder spread over the bottom of a tray. Prouty also experimented using flour instead of plaster of Paris. He obtained the same general effect by having a layer of modeling clay spread over the bottom of the tray and a layer of plaster of Paris above it. In 1977, Raymond Kaczorowski tested the wind and water hypothesis promulgated by Douglas Johnson. Kaczorowski constructed a shallow circular pool on a sandy surface and set a fan to blow over the surface of the water. The caption of this image from his 1977 thesis says that the model lake changes from circular to elliptical perpendicular to the influence of opposing winds alternated every 15 minutes for a total of 4 hours. Although Kaczorowski stated in his thesis that the pool of water changes from circular to elliptical, overlaying the pool with an ellipse shows that this is not true. The resulting pool is too pointy at the ends and too fat in the middle. Wind action certainly changed the shape of the pool, but it did not produce an ellipse. Kaczorowski's thesis has been widely referenced in publications proposing the Aeolian and lacustrine formation of the Carolina Bays, even though it was never published in a peer-reviewed journal. Since his first research in 2005, Michael Davies has promoted the concept of distal ejecta in the form of a frothy mixture of sand and water. According to Davies, the Carolina Bays are the residue of bubbles of gas that deflated during deposition. Their elongation is a manifestation of the energy level and the momentum of the sand sheet as it slides to a stop. Davies's experiments demonstrate the traces left by the bubbles on different substrates. The glacier ice impact hypothesis proposed that the Carolina Bays and the Nebraska rainwater basins were made by secondary impacts of glacier ice ejected by a meteorite impact on the Laurentide ice sheet approximately 12,900 years ago. The impacts of the ejected ice chunks with energies of 13 kilotons to 3 megatons liquefied on consolidated ground, and the ice projectiles created conical cavities inclined at about 35 degrees that were remodeled into shallow elliptical bays by viscous relaxation. 2 books describe the glacier ice impact hypothesis prior to its publication in 2017 in the peer-reviewed journal Geomorphology. The book Killer Comet introduced the hypothesis in 2014 and focused on the mass extinction that accompanied the formation of the Carolina Bays. The book Solving the Mystery of the Carolina Bays, published in 2015, discussed the quantitative deductions that can be made about the Younger Dryas extraterrestrial impact from the geometry and the emplacement of the Carolina Bays. I used pottery clay in my first attempt at modeling impacts. This video shows the cavity created by a stone dropped vertically on relatively viscous clay. After the cavity was made, I started shaking the table to see the effect of viscous relaxation. The depth of the cavity started to decrease from the bottom up because hydrostatic pressure is greater at the bottom of the cavity. I used tiny pebbles for my first oblique impacts on clay. I was able to verify that the oblique impacts created inclined conical cavities that produced shallow elliptical bays with raised rims after viscous relaxation. I wanted to test impacts of ice chunks on a material similar to the sandy soil along the Atlantic coast where the Carolina Bays are found. My first attempt failed because saturated sand packs tightly and the ice projectiles just bounced off. I needed to simulate the soil liquefaction that happens with seismic tremors of magnitude 6.0 or higher. I accomplished this by combining clay, sand, and water and mixing well. The The clay keeps the sand grain suspended long enough to conduct the experiments. This is a video of an ice impact on the sand-clay mixture covered with a thin layer of colored sand. I used a slingshot to fire the ice projectile toward the target. The excavation happens in a fraction of a second. Slow-motion video shows an expanding circular seismic wave from the point of impact, the formation of an oblique conical cavity, the ejection of mud in ballistic trajectories, and the final resting place of the ice projectile at the distal end of the cavity. Viewed from above, the inclined conical cavities have the elliptical shape characteristic of the Carolina bays. This can be confirmed by overlaying the cavity with an ellipse. The raised rims are outside of the cavity. The impact experiments help to answer the question of how the overlapping Carolina bays formed while retaining their elliptical shape. Viscous relaxation decreases the depth of adjacent conical craters to form the elliptical base, and the overlaps follow the geological principle of superposition, in which newer features cover older features. Shake tables are available commercially. Many universities use them to test the performance of engineering structures during earthquakes. The use of a shake table to liquefy samples of saturated sand from the Carolina bays may eliminate the need to add clay to the experimental target mixture. Ice ball guns are used commercially to test the strength of automobile glass, solar panels, and roof tiles during hailstorms. Guns capable of accurately firing ice projectiles of various sizes and at various angles and speeds would be much better than a slingshot. This type of equipment is necessary to increase the scale of the impact experiments beyond the desktop models. Look at this image carefully and notice how the bays overlap. Some large bays have several small bays within them. With the proper equipment and a lot of hard work, it may be possible to simulate the creation of this landscape and prove once and for all that the Carolina bays were formed by impacts. The relative sizes of the ice projectiles could be calculated using the yield laws relating energy to crater size. I hope that there is an inventor out there who can design ice ball guns for geological research.
Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.